So when we're looking at extrema, this is the same thing as what we were kind of talking about. Well, it's been a while, I guess. So when you're looking for extrema, we want to know when is dy dx equal to 0. So for here, we're going to be doing the same sort of thing. So nope, dd theta, because this is theta, of y equals d theta of theta cosine theta. Okay, so we want our dy d theta to be 0, and dd theta of the right hand side is going, that is actually what my name is. So my popular name goes around is, I don't have it here either. I need to get it from my office, but we have been banned from going to our offices for the last year. So one of my friends actually found the Obi-Wan Kenobi Pez dispenser in some store somewhere, and she like was walking down the aisle and was just kind of stopped and went, like something was staring over her shoulder at her, and she's just like, what is that? And looked over it, and there's just a wall of my faces looking back at her. She was like, that is the creepiest thing ever. So she immediately bought me an Obi-Wan Kenobi Pez dispenser. If seriously, if you look it up, my stream name is, or my account name is Obi-Wan Pez, specifically for that. But I decided if I was going to have like a brand or something, I didn't want Lucasfilm and the Pez company to come after me or something. So yeah, good times. Anyway, it's weird because both Ewan McGregor and I look a lot like the Pez dispenser, but I don't really look like him all that much. Anyway, so when we take the derivative of theta cosine theta, we're going to look at this as a product rule. So we're going to take the derivative of the first little bit there. So d theta is just going to be 1 times cosine of theta plus, then take the leave the first part and take the derivative of the second part, which is going to be a negative sine of theta. Volume doing okay? Just out of curiosity. So when is 0 equal to, this is the cosine of theta minus theta sine theta. All right, so let's add theta sine theta to both sides. And then divide both sides by the sine of theta. This is implicitly defined, so like it's not really going to work a whole lot, but theta is equal to the cotangent of theta. And I believe, if I look at what we had here, yep, okay. This is what the answers that Soul Reaver had show, is that theta equals the cotangent of theta. So it is entirely implicitly defined, and you're not going to come out with anything really better, unfortunately. So then we have to figure out what this is going to be. So right. So we can do this numerically by plugging it into some sort of program. I've been using Desmos lately just because it works and it's fine. It's not my necessarily best choice, but does work pretty well. Okay. So if we look at x equals cotangent x, or theta equals cotangent theta, however we're going to do this, and we look specifically on one domain. Let me figure out how to get my window. I don't know that I want to do that. Sure, let's try it. Display 2. Alright, infinite Pez. And we'll pull this up here. Nah, that's not going to work. Alright, whatever. It's fine. It's fine. Let's drag that up there, because I'm being a pain. But, at any rate, so what we got here then is from, we're doing this with pi over 4, sure, why not? We wanted answers between negative pi over 2 and pi over 2, so we've got two answers, here and here, where x equals the cotangent of x. Alright, now we've got theta equals, or theta is approximately equal to, this is negative 0.86 and 0.86. Okay. Actually, we'll just hide that one. Okay. So I don't really have a whole lot pre-orchestrated for this one. And yeah, silly me, I forgot to check my email for anybody who actually sent in problems. Thank you. So what I'm looking at is probably do any problems that you're interested in, do any problems that anybody wants to request, and then also I'd said I wanted to look at doing, if nobody else has anything, I'll probably do function transformation. Yeah, so I tried, at least I tried looking for it earlier, and I couldn't find a math tag, but maybe that's just me, I don't know. I was using the OBS widget, and I did the stream manager, and I couldn't find an actual tag for it. What is going on there? Oh no, wait. That's weird. Okay. My stream preview on my other screen just has the splash screen from the very beginning, so I sometimes get a little paranoid. But my phone is still showing the original, so that's good. Oh, hey, yeah, there is one. Cool. It's not really an educational game, though. Okay, whatever. We'll see if this works. right, so yeah, we got a positive and a negative 0.86, and that worked for us. Whew. Where'd that one come from? Okay, so anyway, if you wanted to then find out which of these was the min and which was the max, you've got kind of two options that you can do. One is you could take a second derivative and do the test off of that. So option one, yeah, not really. At least I don't know one. There could very well be another way to solve this particular equation, but yeah, theta equals cotangent theta, because it's so simple and it's also implicitly defined, it makes it really difficult. So option one is take the second derivative and do the second derivative test. So figure out at x equals plus or minus 0.86. Are these concave up or down? Option two would be like, it's a little silly, but find values around them and see what you're going to get immediately surrounding these values. You do have to be careful with that one, because if you, I guess we already know where, never mind. We know where the, we already know where the mins and maxes are going to be, so you can't have any more places where it comes up or down beyond that. Since the original function is theta cosine theta, we're also in a continuous region, so you're not going to come out with anything that is discontinuous. So those have to be the only two critical points in that area. Option three. Look at the first derivative values around them. And you say, is the first derivative going to be positive or negative around each of our critical points? So there's a lot you can do. Negative 0.86 and positive 0.86. Again, we know are the critical points. So again, depending on how you want to do this, we've got immediately surrounding this, we had negative values. Go back to Desmos here. I'm just going to take a quick peek, not actually change it over. Okay, so if we did the actual derivative function, which is the cosine of x minus x sine of x, so y prime was cosine theta minus theta sine theta. And again, here you pick values for test values that are around these particular values. So that's actually kind of silly. So why not do pi, negative pi over 3 and pi over 3? You could do pi over 4. Not really, because that could be within. All right, so negative pi over 3 and pi over 3. 0 is easier to do, so we'll just do that one here. This is going to be 0 here. This is going to be 1 there. So y prime equals 1 at 0, so this is positive. Which means that our original function, theta cosine theta, is going up in this region. And in our negative pi over 3, let's see, cosine of the negative pi over 3, it's going to be the same as the pi over 3, minus, nope, negative pi over 3, sine of negative pi over 3. This is going to be positive, and this is an odd function, so that's going to come out and make it negative. This is an even function, so it doesn't really matter whether it's positive or negative, pi over 3. Cosine of pi over 3, of course I'm going to have to draw the triangle. I haven't done trig in like months now. Yeah, so that's 1, 2, root 3 here. Cosine's going to be a half. Shameful, I know. All right, minus pi over 3 times the sine of pi over 3 is going to be root 3 over 2. Got to remember to exaggerate my pen lifts on these. Is y prime at negative pi over 3. All right, is 1/2 minus pi root 3 over 6. Well, I don't know what that is. Pi over 6 is pretty close to a half, so then pi root 3 over 6 should be greater. So that should be less than 0. Just double check. Oh yeah, very negative. It's like 0.4, so we're negative 0.4, so we're good. So this one's negative, and probably by symmetry here we can say that pi over 3 is also going to be negative. So if we look at this, cosine of pi over 3 was the same as the cosine of negative pi over 3, so it's also 1/2. Y at pi over 3, y prime at pi over 3 is going to be 1/2. Oops, I'm off. Yeah, I'm way off. I gotta stop doing that. Come on. No. This is one of the problems with... You gotta make sure that you know your hardware. Completely forgot. Alright, I'm slowing down a bit. So unfortunately, if anybody else is slowing down here, I apologize. My computer is not behaving right now. Okay. So then we've got a minus positive pi over 3, but this is times the sine of pi over 3. So yeah, this is symmetric. So this is also going to be less than 0. Just going to make that negative. So since we're going down then up, that means that negative 0.86 is going to be a minimum. And 0.86, since we're going up and then down, this is going to be a maximum. All right, so that is what we had in the answers there. Cool. So let's look at this real quick. Find partial derivatives with respect to x, y, and z, and then add them. So it looks like you are actually looking for the, what is that? divergence. It's been way too long since I've done that. No, gradient. Looks like you're looking for the gradient of that particular equation. I'm not super great at pure math or analysis. Um, my degrees were in math education and applied math. So a real analyst would be like, ugh, you're one of them. Not really, but I definitely don't do any like actual research. Okay, so yeah, gradient specifically looks at like gradient of f is going to be take the partial of f with respect to x. No, because this is going to be vectors. So it only does it in the I direction. Plus, it's been way too long since I've done this. So yeah, don't quote me on it. I mean, what am I doing, right? I have a book right next to me. I have the entire library of the internet. Yeah, so this is gradient. Yeah, okay. But usually you're looking at this not as just an f. This is a gradient of a vector. So anyway, it's mostly out of the out of what we're doing here. All right. So, but you said r squared is equal to x minus a squared plus y minus b squared plus z minus c squared. Took that one on faith. All right. So yeah, if you're taking this, you want to look at what are the derivatives, partial derivatives you said, and then look at each of them separately. So r is radial, so we can take its partial derivative with respect to all three of these. Certainly hope so. All right. ddx of r squared equals ddx of x minus a squared plus ddx of any function of y and z, doesn't even matter what it is, this is just going to be 0. And then you said ddy of r squared is going to be equal to ddy of y minus b squared plus ddy of a function of x and z is again going to be 0. ddz of r squared is equal to ddz of z minus c squared plus ddz of a function of y and x and y. So again, that is going to be 0 here. Okay. All right, now again, assuming that r can be a function, well, I mean r technically is a function of x, y, and z in this case, and that's okay to do here with this particular notation. Then we're looking at 2r dr dx. Sorry, that should not be, that should be like an arrow. Okay, there we go. All right, and that is equal to then, this is going to be 2 times x minus a. And since we're taking the partial derivative with respect to x, there's nothing to be done there. It's all just 1. And same stuff with below. So this is going to be perfectly symmetric again. dr dy is 2 y minus b, and 2r dr dz equals 2 z minus c. All right, in all of these cases, the 2's are going to divide off from both sides. We're just left with 1's there. And then r's, I mean, I guess we can just, okay, can divide over and then substitute that nasty square root thing that's going to be here. I don't know if we want to do that, but all right, cool. It's like you were looking at dr dx plus dr dy plus dr dz, I think is what you said, which is going to be equal to, this is x minus a over r plus y minus b over r, yeah, plus z minus c over r. So this is the sum of x, y, and z, and the minus the sum of a, b, and c. Looks like, if I'm reading that right. Weirder things have been known to happen. So plus y plus z minus parentheses a plus b plus c, all divided by the square root of all that stuff. Well, good. Guess that proves I know something. Certainly not everything. All right. So yeah, second partials, because it was divided by r, not r squared. So because we had these r's here, we divided them over, and then, right, so up here we had r squared, but down here we only have r. Righto. What else we got? Okay, so if you want the second partials, then you're going with well, you're unfortunately going to have to get used to them if you're going to be doing anything in like physics or higher math, because they come back a lot. Differential equations, they come back a bunch too. It's kind of interesting because I was teaching DiffyQ last semester, and I had to teach my DiffyQ students who had never had Calc 3 how to do stuff, and I'm like, okay, this is kind of interesting. And they were just like, all right, well, you say it does that, I guess I'll believe it. I'm like, Not quite the point, but alright, cool. Alright, so if we take the second derivative, or we just take the derivative of both sides again. So this is easier. It's going to be take d dx of r dr dx, and then take dx dx of x minus a. Alright, so that side is just going to be 1. And then this side's going to be much bigger than that, so I don't know why I did that. Alright, so this side is going to be, take the derivative here, we get dr dx times dr dx. That's just multiplied by, not second derivative. Then we take r times, now this is the second derivative of r with respect to x twice. Curses. Alright, so then d squared r over, I shouldn't say that. It's not. It's second derivative of r with respect to x is going to be 1 over, this is partial of r with respect to x, parentheses squared, plus r. And yeah, by symmetry, because it's the same thing. I'm just not going to spend time. It's going to be second derivative of r with respect to y twice is similarly going to be 1 over dr dy squared plus r, and second with respect to z is also going to be 1 over, keep losing my cursor, dr dz squared plus r. Yeah, says it's doing fine. I don't know, that's weird. So if we take the sum of those, then this is going to be the second partial of r with respect to x plus second partial of r with respect to y twice, plus second partial of r with respect to z twice. It's going to be equal to those fractions. So 1 over dr dx squared plus r plus 1 over dr dy squared plus r plus 1 over dr dz squared plus r. Not thinking I like this very much, but you know, it works. So all of this stuff is going to be equal to, this is 1 over dr dx is x minus a over r parentheses squared plus r plus 1 over, you know what, let's just let's just dot this for a second and say by symmetry it's going to be this stuff again. So here I would want to probably multiply everything by r squared, top and bottom, and so this would be like r squared divided by x minus a parentheses squared plus r cubed, and the same for the other two. Hmm. That could be fun. So this is going to be r squared times y minus b squared, y minus b parentheses squared plus r cubed times z minus c parentheses squared plus r cubed plus r squared. I should have just left that out, huh? X minus a squared plus r cubed times z minus c squared plus r cubed plus r squared x minus a parentheses squared plus r cubed. Yeah, I'm out of room, but oh well. Y minus b, we know that that's the same stuff, squared plus r cubed. All divided by, this is all of those things multiplied together again, so x minus a squared plus r cubed, y minus b squared plus r cubed, z minus c squared plus r cubed. Alright, so I think I'm going about this in a very roundabout sort of way, and there's probably a better way to do this. But I think for what we're doing, this is probably this might be enough. Not sure I want to go any further. Did you get any further than that? Allegedly either 2 over r or 3 over r. I mean, I can believe it, but I can believe it, but I don't know if I want to go any further. There's, in all honesty, there's probably a bunch of stuff that like cancels out, and well, right, if you took a different route to get here, then there's very possibly some nicer stuff that drops out and makes much nicer things. But I mean, yes, but so do I. Don't feel bad. All right. Right, because that's there. See, this is the problem. Now I want to get it right, but this is going to take so long. Anyway, let's hello all you viewers out there. I have Barrytron, Commander Root, Gojigi, RGPT, Soul Reaver, and Violets. Welcome. Soul Reaver is one of my regulars, so you know. Yes, so hyperbolic sine, cosine, tangent are very useful when you're looking at. Oh, okay. Oh, that's you, right? Oh no, never mind. No, not you. Sorry. Anyway, put that there as a warning to the rest of the problems. Okay, so yeah, the hyperbolic functions are pretty nice. You see them a lot more when you're talking about what are called catenaries, which are like if you take a length of rope or chain or whatever and tie them up in two places, you will get a uh, a curve which is not a parabola. And so it's a little weird because it's like, well, it should be a parabola, right? Because gravity's pulling down and it's doing all this in theory, but the thing is that the way that it pulls, because there's more weight in the center and the tension kind of holds it and tries to pull it side to side a little bit, it lengthens it out a bit and it makes this catenary. I'm probably saying it wrong now that there's actually like people watching the channel. No, it's okay. Yeah, catenary. So, like I said, it's because there's weight pulling more, pulling the center more down, but at the same time, it's also pulling tension side to side. So it makes an interesting shape. Okay. And there's some really cool physics behind it, but this is like, I'm going to regret this, but right, should be that one. Yeah. Oh, ew. Trying to display all sorts of stuff on the... Yeah, so this is the hyperbolic cosine of x, and it can be generalized using a's here, 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 and here. So the hyperbolic cosine of ax is equal to e to the ax plus e to the negative ax over 2a. It's been a long time since I used those, but I mean, I teach pre-calc, so it's not that surprising. Yeah, so hyperbolic sine should have a negative here, which at 0 causes it to be 0 because it's going to be e to the 0 minus e to the negative 0, or e to the 0. Yeah. And the other nice thing about hyperbolic sine is that like you get very similar properties between the hyperbolic sine and the hyperbolic cosine that you would with the sine and cosine. So not exactly the same, but similar-ish. So you'll notice if you take the derivative of either one of them, the negative from the e to the negative a is going to come down. It's also going to mess up the a's because you're going to have a's all over the place. But yeah. But the negative, if you're just looking at like e to the x plus e to the negative x over 2, the negative from the e to the negative x is going to pop down, and then it becomes a hyperbolic sine. And then when you take the derivative over here, the negative pops down, and it becomes hyperbolic cosine. So it actually is a two-cycle between hyperbolic sine and hyperbolic cosine when you're repeatedly taking derivatives, unlike the regular sines and cosines, which are a four-cycle. So it takes, sine to cosine to negative cosine back to sine. I took a class in junior year, which was called Abstract Algebra, which at one point we had a lot to do with cycles and finding the properties of cycles. So again, oops, not partial. Dx of the hyperbolic cosine is equal to the hyperbolic sine, and hyperbolic derivative of the hyperbolic sine is equal to the hyperbolic cosine. So this bounces back and forth, and so this is I shouldn't do that. This makes a 2 cycle. Yep. And, just like when you're taking the subsequent powers of I, right? So I to -1 to -I to, 1, and back to I makes a 4 cycle. We learned that, way a long time ago. But, yeah, it's interesting when you start looking at like derivatives that make cycles.